My name is Katy Croff Bell. I'm the director of the Open Ocean Initiative at the MIT Media Lab and also an explorer with the National Geographic Society. My background's in deep sea exploration, and so the talk that we're going to go through today gives you a little bit of history of deep sea exploration, some of what's going on today, including some of the places that I've been, some stories of exploration and discovery of unexpected things, and also some of the projects that my group is working on at MIT, and really how I see this moving into the future. So I will share my screen and we can get rolling. How does that look? We good? All right, I'm going to carry on and stop me if it does not look good. So deep sea exploration. So first, we'll go through a very, very brief voyage through time. It's far from complete, but we'll kind of give you a sense of how progress has been made over really more than 2,000 years. People have been trying to get to the deep sea. So one of the first documented instances of deep sea exploration, and really probably not that deep, but of use of a tool for someone to get deeper than they could just by holding their breath and swimming down. There are numerous legends of Alexander the Great being lowered into the sea into a glass barrel, and this was probably in the mid 3rd century BC. And then you fast forward many, many hundreds of years, and Ferdinand Magellan in 1521 tried to measure the depth of the Pacific Ocean with a 2,400-foot weighted line, but of course could not find the bottom. So only about 700 meters worth of line, and it's now very obvious to us that there's no way he's going to reach the bottom with that amount of line. In the 1600s, 1620, Dutch engineer Cornelis Drebbel built the first navigable submarines. He built 3 of them, and his 3rd model could hold 16 people and go to about 5 meters deep. This is an illustration of it in the Thames. He had been working for the British Navy at the time, and it was had a sort of wooden structure with leather over the top and had oarsmen on the inside to propel this vehicle. Another 100 years later, and John Lethbridge built a completely enclosed suit to aid in salvage work. So, you know, many naval battles, a lot of salvage work. He wanted to get stuff back from the ships that had gone down. This is a one-man suit that could go down and aid in being able to A, go deeper, and B, stay down longer, which is always what people want to do. Again, looking at what, just what is the depth, what is the shape of the ocean. In the late 1700s, early 1800s, Laplace calculated the average depth of the Atlantic Ocean to be almost 4,000 meters just by observing the tidal motions on Brazilian and African coasts. It's amazingly close. If you look up average depth of the Atlantic, you get answers anywhere from 3,300 to 3,600. So he was pretty spot on, and obviously proved that you need well more than 700 meters worth of line to get down there. And then we fast forward again to the HMS Challenger. And this ship is often considered, and this voyage in particular, the 1872 to 1876 voyage, is often considered the first modern oceanography expedition. They circumnavigated the globe, spent 3.5 years doing almost 500 deep sea soundings, over 100 bottom dredges, 150 open water trawls. And they discovered 715 new genera of marine organisms and more than 4,400 new species during this time. And so this has really laid the groundwork for the next a couple hundred years, 150 years, whatever we are now, of oceanography and ocean exploration. And then we get into how do people, again, get deeper, stay down longer. In 1930, Beebe and Barton were the first humans to reach the deep sea, and the definition of deep sea is sort of more than 200 meters. In a bathysphere, which is basically just a big metal sphere. So they reached a depth of 435 meters, where they observed jellyfish and shrimp and deep sea fish. And they actually weren't taking notes of their own. They had a line up to the surface vessel, and an illustrator was sitting on board, not seeing what they were seeing, but they were describing what they were seeing, and she was drawing it up on the ship. So any images that you see from this sort of first dive into the deep sea was by somebody who wasn't actually seeing what was going on down below. It's quite incredible. A few decades later, Jacques Piccard and Lieutenant Don Walsh set a new record of 35,800 feet aboard the Trieste in the Mariana Trench. And this record was held until just a few years ago, really, when James Cameron went down for the second time. And since then, several other people have been down to the bottom of the Mariana Trench, but this record held for over 50 years. And the amazing thing about this is the people were actually in that little sphere that you see down at the bottom, and the entire upper part is full of jet fuel. So that was their buoyancy. And they had weights on the bottom of the, so the two, not sure if my cursor, you'll be able to see. But anyway, they had weights on it to get them down, and then they had to let go of a whole bunch of lead shot to get back up to the surface. And it really was just down and up, and that was it. And then a few years later, we got a little bit more maneuverable with Alvin in 1964. Alvin is a crewed deep sea submersible owned by the US Navy and operated by the Woods Hole Oceanographic Institution. There were actually 3 of these vehicles that were built around the same time. Alvin is the only one still in operation today, and is used less so by the Navy, more so by the scientific community. And now going back to just what does this deep sea look like? In 1977, Marie Tharp completed the very first map of the entire ocean floor. She used seismic data collected by Bruce Heezen. She was not actually allowed to go on the ships herself because she was a woman. But all of this data was coming back, and she was the one who was putting it together and making the maps, and discovered the mid-ocean ridges. Initially, it was dismissed as girl talk, but now we know that almost everything that she drew is actually there. And it's quite incredible. And it's taken until now with satellites to be able to update those maps that she created for the very first time in the 1970s. And just less than 10 years later, we get into robotics. So the first fiber optically cabled deep sea robot was Jason Jr. This again was built by the Woods Hole Oceanographic Institution, designed to build and used to explore the Titanic the year after it was discovered. And really the groundbreaking thing about Jason Jr. was that it proved that deep sea exploration could in fact be achieved through unmanned robotics, which had never been shown before. And that's really what takes us into how we've been doing it for the last 20 to 30 years, and really where we are today. So you take those seismics, you take those estimations of depth based on tides, and how do we really do it today? So when you see maps of, let's go forward just a sec, of the entire ocean, it looks like it's incredible detail, but the resolution is still only about 1 kilometer. And that's because we're using satellite altimetry, and that's looking at the shape of the sea surface to calculate the shape of the sea floor. And the best resolution that we can get today is a horizontal resolution of about 1 kilometer, which is great when you're looking at a map at this scale. But if you're trying to put robotic vehicles down, for example, it's not really good enough. You still need ships or other vehicles to be in the water to get more precise bathymetric measurements than that. So you have vessels going at a maximum of about 10 knots, who have multi-beam sonar systems that can sort of paint a picture of the seafloor using acoustics. And that's how you can get resolutions of meters to tens of meters of seamounts, other features on the seafloor that are really good enough to be able to be confident to send your remotely operated vehicles or autonomous vehicles down. And once you have a map of an area that you are interested in, that's when you send your robots down. So these are various examples of remotely operated vehicles, or ROVs. In the upper left is Hercules, that's a science class ROV. In the upper right is an oceaneering vehicle. So this is really a work class. This is like would be working on an oil and gas platform, for example. In the bottom left is one of the smaller vehicles that might be used for inspections or something like that. Not super capable, but much smaller and much easier to be able to deploy. With the ones on the top, you need a big ship, you need a crane, you need an A-frame. Excuse me. You need a lot of specialized equipment to be able to operate it. And then in the bottom right-hand corner, you can see a student. This is a high school student working on an ROV that is made out of Legos. So Lego robotics and computer fans for propellers. So there's quite a broad spectrum of capabilities and requirements for ROVs these days, from toys all the way up through multi-million-dollar vehicles. I saw that you've had a lot of talks about autonomous vehicles, so I won't go into too much detail about these, but you can see that autonomous vehicles, again, are quite large, mostly require bigger vessels, a lot of support equipment, and are often quite expensive to purchase and then also to operate. Some are more the scientific and experimental, like Sentry up in the upper left, and then the other three are commercial vehicles that you can buy from Hydroid, Bluefin, Hugin. There are several companies around the world that manufacture these now, which has really only been around for about 20 years or so. Bluefin was, I think, the first commercial autonomous vehicle manufacturer. And that actually was a spin out of MIT Sea Grant. If you want to look at an area sort of consistently over time, underwater cabled observatories have become more and more prevalent. So this is one off of the west coast of Canada, of British Columbia, that is operated by Ocean Networks Canada. So you can see that it goes from land. They have laid thousands and thousands of miles of cable and have these nodes. So the yellow thing at the bottom is what are their nodes that provides power, sensors to all the sensors that are located on the seafloor. So this allows you to take measurements through time, which, you know, a ship with an ROV often does not. You're always going to new places. You're always looking for new things when you are have a ship that's constantly on the move. Excuse me. So one example, to go into a little bit more detail, of one of these systems. So this is the exploration vessel Nautilus. I was the chief scientist and vice president of the Ocean Exploration Trust, which is the nonprofit that owns and operates Nautilus. for several years. And this is sort of the state of the art. Nautilus, there's a US government, a NOAA ship called the Okeanos Explorer that has very similar capabilities to Nautilus. The Schmidt Ocean Institute has the research vessel Falkor. So there's several ships, not too many, but more and more are starting to have the similar kinds of capabilities in terms of seafloor mapping with multi-beam remotely operated vehicles, and also telepresence. So this little video gives you an idea of, you've got your crane and your A-frame on the back of the ship, and then it goes down to your vehicles. This is a 2-vehicle system. Hercules is neutrally buoyant, sends data, video up to Argus, which then sends everything back up to the ship where you have your team working on board, as well as a satellite dish so that you can send video, data, audio, excuse me, all back to shore. And this is the Inner Space Center at the University of Rhode Island, which then is distributing that, that data, that video all over the world. So Nautilus was one of the very first ships that had this capability of telepresence. And you can go to the Nautilus. I don't think they're live yet because of COVID, but Nautilus Live is the website where you can go to see a live stream of deep sea video from wherever they happen to be. The ship is based in the Pacific now. This video is actually from Gorange Bank, just off the coast of Portugal, where we ran into this goosefish that we probably watched it for a half an hour, just chowing down on all those little fish. It was very fun. So this allows us to share what we're doing live with literally thousands to millions of people all over the world, both for education purposes and also for scientific purposes. So this is the inside of the Inner Space Center. So you can have a team who's working here and interacting really closely with the people who are on board the ship. And also there are what's called exploration command centers, which are set up at various universities and research institutions around the world, so that people can, and by people, I mean specifically scientists and engineers, can get even more data than you could if you were just watching the public video feed. So they can actually participate from their home institutions. The bottom right, you don't really need to be able to read. That was just the landing page of being able to access dive plans, dive reports, the data, navigation, et cetera, et cetera. So they're, excuse me, online collaborative tools for them to be able to participate in a meaningful way. So Nautilus's first cruise was in the Mediterranean in 2009, and we spent a lot of time in the Eastern Mediterranean and then across to the Western and a little bit out into the Pacific over the course of 4 years. So here are a few highlights of the places we've been. This first video is from the Southeast Aegean Sea, just off the coast of Turkey, where scuba divers had actually spent many, many years finding shipwrecks, but obviously you can only go to a certain depth. And then we started doing a side scan sonar of the area and found dozens and dozens of shipwrecks. So this is one of the ancient shipwrecks that we found, probably about 1,500 years old or so. And you can see that all these jars are extremely uniform. This would have been probably a cargo ship that would have carried wine or oil or some other cargo in the Aegean Sea and possibly elsewhere in the Mediterranean. You can also see that the wood, there's no more wood, no more really evidence of the ship itself. You can really only see the ceramics. And this is pretty typical of ancient shipwrecks in the Mediterranean. All the wood, all the organic material is gone, and all that's left is these amphoras. In Greece, we We're focused more on the volcanology. So spent a lot of time in and around Santorini volcano, and actually just northeast of Santorini, about 5 kilometers or so, is an underwater volcano, which is today probably much more active than Santorini itself. And we found for the first time this hydrothermal system. And you can see the orange and the white are different types of bacteria that are growing on the hot hydrothermal fluids that are coming out of these vents. So these are very large chimneys that had formed from the hot mineral-rich fluids coming up out of the volcano, out of the seafloor. You can sort of visualize it a little better now. You can see all those bubbles coming up. That's full of carbon dioxide. And because of the very, very high rates of carbon dioxide, the pH of the basin of Colombo is very, very low. It's extremely acidic. We saw no fish down here or much other macrofauna. It was all bacteria, and you can see all that orange flocculent matter floating around. Hercules is also outfitted with a high resolution mapping system. And this is the work of Chris Roman at the University of Rhode Island and in his lab. So this is a downward view of the northern area of Colombo crater. And again, you can see those white streaks, and that's probably indicative of hotter waters versus the more orangey bacteria on the seafloor. And here's another sort of side view. You can see the chimneys, and this was done. You can also kind of see the path that Hercules made as we were collecting this data. You have to go back and forth and back and forth. You can't get all of this data in one pass. So it probably took several hours to collect all the data and thousands of images to be able to create a map like this. But it's extremely high resolution, probably on the order of centimeters, if I had to guess. And so you can see the scale of satellites, 1 kilometer resolution, ships, 1 to tens of meters resolution, depending on your water depth. And then once you get robots in the water, then you can get extremely detailed centimeters to, in some cases, millimeters, depending on your sensors and visibility. Now, in the Straits of Sicily, we were also looking at volcanoes, or hoping to. This is an area where the seafloor is spreading apart. So you have a spreading center here, and there had been documented cases of lava balloons floating up off of the coast of an island called Pantelleria. So that's what we were looking for off the Straits of Sicily. And we did find it, but we also came across something quite unexpected. We didn't know what it was, but there were people on the island of Pantelleria who were watching the live feed as we were finding this airplane. And they told us that there had been a battle during World War II, the Battle of Pantelleria, between the Italians and the British. And it turned out that this was one of the 2 planes that had been shot down by the British. So it was an Italian plane. And so we were able to send this data to the Department of Antiquities in Sicily, so that now they have it and have all the information that we had collected associated with this airplane. So after about 3 or 4 years in the Mediterranean, the ship came over to the Caribbean and Gulf of Mexico. So you can see all the places that we went. I'll share just a few of the stories with you. I said previously that, is this gonna work? There we go. Cabled observatories are really the only way to go back and look at the same thing over and over again, but you can actually go back to the same place with ships and robots. And EcoGig is a project that was following up on the BP oil spill that happened in 2010. So they were going back to, in fact, the same exact corals year after year to document what had been happening to them. what were the effects of the oil, what were the effects of the dispersants on individual corals over a long period of time. So you can see some of the tools they brought with them, a very high resolution camera, the magic wiffle ball wand, and various other sensors to be able to measure and take samples of these corals so that they could document what was happening. Also in the Gulf, there had been during a pipeline survey, and an oil and gas pipeline survey, there came to be a couple of interesting targets that were turned over to NOAA. The Okeanos Explorer, the NOAA ship, went and took a look and found that this was in fact a shipwreck, but they didn't have the capabilities to be able to collect any of the artifacts and do the kind of detailed studies that Nautilus was able to do. And so we went back a couple years after it was first discovered, excuse me, and found that this wreck had been, had gone down probably before Texas was a state, which might not mean much to many of you in Europe, but was very exciting for us in the US, being a much younger country than you have. And you can see some of the artifacts that are there. The shape of the ship is still there, the anchor, the cannons. And there were also two other shipwrecks in very close proximity that seemed to be carrying cargo. This one that you see here seemed to be pretty heavily armed, and the other two were not. And the archaeologists think that this one may have been escorting the other two back to port when they got hit by a storm, possibly a hurricane in the Gulf of Mexico. And one final Gulf of Mexico story. This was a project that was looking at the fluid dynamics and the chemical dynamics of natural oil and gas seeps. So Hercules was just going down for a dive. They were doing all their routine checks on all the sensors and cameras and things. And you'll see in a moment what they came across. If you had ever asked me if we would ever see a whale or any other kind of marine mammal with Hercules, I would have said there was no way, because these vehicles are pretty loud. And I would have thought that they would have scared off anything like a marine mammal. But this sperm whale came across Herc at several hundred meters deep and was swimming around and around and around for a good long time. It was amazing and completely unexpected. One of the things you have to always remember is to expect the unexpected in deep sea exploration. So another unexpected discovery was when we were looking at Kikum-Jenny. This is another underwater volcano, and it's off the coast of Grenada. And we had spent a week or two studying the volcano itself. Inside looked very, very similar to Colombo, actually. One of those first videos that I showed you, a lot of orange bacteria, all kinds of things living inside. It's a little less acidic, so we did see fish and other organisms swimming around in Kikum-Jenny. But we also noticed that it looked like there was a landslide down the west side of the slope of the volcano that looked kind of interesting. And we decided on one of the very, very last days, if not the last day, to go take a look and see if we could collect some samples to determine when this landslide would have happened. Oops. And I don't appear to have that video, but we found a chemosynthetic ecosystem down there that had been growing on organic rich sediment and fluids that was probably being squished out of the sediments from Venezuela and northern South America. And we found mussels that were at least 14 inches, and that's probably 28 or so centimeters long. These are some of the biggest mussels in the world, and they were growing. They were chemosynthetic, so they weren't filter feeders. They weren't collecting things from the water. They were actually using the minerals and the organics coming up out of the fluids to be able to feed themselves. And I apologize for not having that video. If I can find it a little bit later, I'm happy to share it. After spending time in the Caribbean and Gulf, we moved on to the Eastern Pacific Ocean, went up and down the west coast of the US after hitting the Galapagos Rift and Galapagos Islands after coming through Panama. And hydrothermal vents were actually discovered by Robert Ballard and team in 1977 in the Galapagos. So this was sort of a return to the area where these amazing systems had been discovered for the very first time, and proved that life on Earth did not have to be based on the sun and photosynthesis, which had been sort of prevailing theory of the day, that these organisms, the bacteria, the clams, the mussels, can live off of the hot mineral-rich water that's coming up out of these hydrothermal systems. You can see the hot water pumping out of that little tiny chimney right there. The crabs cruising around. So this was a return to that area. They did some high resolution mapping to be able to compare what the hydrothermal field looks like today compared to 40 years ago, as well as some other studies. And there's actually just a paper that came out on the Galapagos work, which happened 5 years ago. And now the paper literally just came out just a few days ago. If you're interested, I can send you the link. And this is a flamboyant squidworm, which none of us had ever heard of. In fact, no one had ever seen one in the Eastern Pacific Ocean. It had only been documented in the Western Pacific. So every time we go down, every time there's an expedition, we're always finding something new. Now, off the coast of California, this actually was not something new. This was a whale that was sunk by scientists at the Scripps Institution of Oceanography to be able to study the progression of how scavengers in the deep sea eat and use whale falls or whale carcasses that sink in the deep sea. So I think this had been sunk 4 or 5 years prior to us going back to it. You can see there's a tangle of line on the right that would have been used for the anchors to get it down. And then really all that's left at this point is the bones. And you can see the white bones with a gray kind of bacteria that's now one of the only things left utilizing the lipids that are still coming out of the bones after several years in the deep. Here you go. There's an anemone, a little fish, and the white on the left are the vertebrae. So this is really meant to give you a very, very broad look at, some of the things that we may have been looking for specifically, some of the things that some of these studies that go back to similar places or even the same exact organisms year after year, and some things that were found that were completely new when we were looking for something else. And it's really these deep sea tools that make it all possible. But there are some challenges with how we do things today. And we've got to be very honest about those if we're going to think about how to explore into the future and how to create a new way of exploration. So one of the biggest challenges is that the technology to explore is largely inaccessible to a very large part of the world. It's big and it's expensive to build and operate. So the blue countries are those that have deep sea technology. More or less, there may be some others as well, but this gives you a sense. And it looks like a lot, but that's just because some of those countries are the biggest, the US, Canada, Russia. But in reality, only about 15% of coastal countries have deep sea capabilities, making the deep sea inaccessible to about 85% of coastal communities around the world. So this shows you that 71% of countries around the world have deep waters, and that's greater than 200 meters, but only 15% have access to those deep waters. And by that, I mean the ships, the deep sea vehicles to be able to explore. So this inequity is severely hampering our progress. Not to mention the fact that even with the capabilities that we have, using our current exploration methods, it'll take about 10 to 100,000 ship years to completely view the seafloor at a rate of about $50,000 to $75,000 a day. So we could continue to employ large, expensive assets and making just a little bit of progress each year. But even if we added 10 more ships, you would only bring that estimate down by one order of magnitude. So we're still talking 1,000, 10,000 ship years. So we might get hit by an asteroid before we see the entire seafloor. Or we could invest in new technologies, research methods, and social systems to fundamentally transform what it means to explore and discover in the 21st century. So I think that we need to create a new paradigm for ocean exploration, and I'd love to hear some of your thoughts on how we can do this. But I think that we need a spectrum of platforms and tools and really an effort to make ocean discovery accessible to all communities around the world. And we need to do that by creating a suite of low-cost distributed systems and supporting a community of explorers around the globe. And by doing that, we would accelerate our understanding of our planet faster than ever before. So today, I think the challenge is that deep sea exploration is inefficient. It's too slow. We simply can't wait. It's expensive, resulting in limited to no access by those who can't afford it. And it's exclusive. A lot of times you need to have a PhD, you need to be from a developed country to be able to get the tools you need. And so we need a new approach. The rate of exploration and our understanding of the deep sea is much too slow to inform responsible management. And you see all kinds of things happening today in terms of deep sea mining and other activities, and we simply don't know enough, I think, to be able to responsibly make decisions. And so we really need a new approach. We need to develop low-cost sensors and platforms. We need advanced data analysis, access and archive, and we need to create a truly global community of explorers. We can't just have people from Western countries going to a place, collecting data and bringing it back with them. We need everybody to be a part of this. And I also want to note the importance of interdisciplinary collaboration to make all of this possible. We need to look at other industries, from commodity electronics to toy makers to storytellers, to truly create a sea change for the deep sea. So I want to tell you about a few projects that my group's been working on related to these three themes. So the first is developing low-cost sensors and platforms, which will dramatically decrease the cost to access the deep sea. So we need to do this in order to maximize the efficiency of discovery. Why create one multi-million-dollar vehicle when at this point in time you have a supercomputer in your pocket? Why can't we create tens of thousands of smaller devices that can go out and at least get a first glimpse at areas of the deep sea, and then you send in your bigger ships, your costly ROVs, that sort of thing. So I want to share two projects with you. The first you got a little preview of a minute ago. This was the Wayfinder project. So my team created Lego-based remotely operated vehicles called Wayfinders that we used for a 2-day workshop with a group of 40 high school students from all over the world. Obviously, this vehicle can't go to the deep sea, but it can be used to get kids interested in ocean science and engineering, which is really important in building a global team in new communities. We need to get the youth involved. We need to get them excited. And right now, we're actually working to push this project a little bit further. Right now, you can see all the electronics and things were in sort of a lunchbox. So right now, we're trying to figure out how to make it more modular so you can build any kind of system you might want, which is more in the spirit of the Lego building system, and also a little more robust. These were, we brought them out to Boston Harbor for a day, which was exciting, but a few pieces fell off here and there. So we want to make them better able to withstand the environment. Another project is called MAKA. That means coconut eye in Hawaiian. It's a low-cost oceanographic camera and sensor platform that enables the exploration of undersea environments using a new pressure-tolerant camera housing. And this has been designed and is currently under construction right now with the MIT Future Oceans Lab. And by low cost, I mean probably a couple $100s, and that completely depends on the scale of manufacturing. Like if we build one, it'll cost several $1,000s. If we build 10,000, it'll cost much, much less. So this system was originally conceived several months ago for educational workshops with a group in Hawaii called the Polynesian Voyaging Society and the Kamehameha schools. So MAKA is meant to allow people to explore and monitor their own marine resources for more than 1,000 meters deep, which is much more than some of the cheaper commodity systems that you might get off the shelf these days. So it's based around off-the-shelf single board computers and readily available microprocessors. The idea is that it'll be inexpensive to produce, easy to program, and simple to use. So this is, as I mentioned, currently in development. We're building our first sort of test run right now and planning to send some out to some of our collaborators around the world to be our first use case testers this fall, which we're really quite excited about. So the second component of change is advancing data analysis, access, and archive. Oftentimes data are not accessible, even if they're technically publicly available, due to users needing to know what to look for, where to find it, how to download it, sometimes needing specialized software to be able to analyze it. So we're working on a couple of projects that aim to address these challenges. The first is called FATHOMNET, and this is in collaboration with Kakani Katija at the Monterey Bay Aquarium Research Institute, Sea Vision AI, a small company in Cambridge, and others. And so we're developing FATHOMNET, which is an underwater training data set and algorithms for automated detection and classification of underwater video using machine learning. So our efforts have used MBARI's video annotation and reference system, which has been developed over more than 30 years, 35 years. So they have thousands and thousands of different terms in their knowledge base and nearly 7 million annotations of underwater video. So it's probably one of the best data sets for underwater video annotation in the world. And we've shown that our tools can be used to not only detect and classify organisms in MBARI's data, but also other organizations, including footage from National Geographic and the NOAA ship Okeanos Explorer. So this video here is actually from the Okeanos, and you can see the little squares popping up on all the different organisms. And this model was used for morphological detection, so things that were fish-like, star-like, not the species themselves, but rather what does the thing look like. So as FATHOMNET continues to develop and incorporate more image data from other oceanographic community members, we hope that this effort will ultimately enable scientists, explorers, policymakers, storytellers, and people in this, growing community that we want to be a part of it, to more fully understand and care for our ocean. How can we use this to train students who don't know what that fish is? Can we use this as a learning tool for a broad spectrum of people? So the second project is the Large Interactive Laser Light Field Installation, or LILY. And this is the basis of an MIT master's student thesis that actually just got submitted a week or two ago. LILY is a 360-degree volumetric aerial light field display. So it uses a combination of lasers and video projectors to visualize oceanographic and meteorological, really any kind of geographically referenced data. You don't have to have a head-mounted display. You don't need to have an Oculus, some sort of VR system mounted to your face. And so the idea is that it's very collaborative, it's very open, multiple people can be a part of it, and it can be used in ambient light conditions. It doesn't need to be in a completely dark room to be able to work. So it was built using a free game engine and includes 4 view zones around the sort of square to allow for a team to have an unprecedented level of situational awareness. And finally, technology alone cannot solve our grand challenges, as much as many engineers like to believe it. The true key is people. So how can we create a global community of explorers? We really need to work outside of the traditional academic structures, not only to increase the number of people exploring, but also the diversity of people. So we need to build new bridges with groups that have not yet been invited into oceanographic exploration, especially developing countries around the world. But even in countries like the United States, there are many, many groups of people that aren't traditionally involved. So we need to look to new communities and build greater global capacity for exploration. So a couple of projects that we have going right now. One is called My Deep Sea, My Backyard, and it aims to enable explorers to discover their own deep sea backyards using low-cost technologies while building lasting capacity. 2 of my colleagues, Randy Rojan from Boston University and Diva Amon from the Natural History Museum in London, ran workshops in Kiribati and in the Pacific Ocean and Trinidad and Tobago and the Atlantic to train local scientists, students, and educators to use drop cameras and small ROVs to conduct their own exploration and to share their discoveries with their communities. So some of the technologies were left in country for the participants to continue using them beyond the end of the project. Some, unfortunately, were just on loan and we had to take them back. But we're right now in the final evaluation phase of this pilot project. And we've learned a lot in terms of what what we need to do in the future to be able to really be successful in this space. Some of those things include having an in-country advocate, really having someone dedicated to the project in country and not just us going to and leaving. Really easy to use technologies, easy to fix technologies, and leaving them rather than loaning them in the country. I'm also working with National Geographic and a company called LINDBLAD Expeditions to determine the feasibility of deploying low logistics systems from LINDBLAD's fleet of vessels. They have about a dozen or so ships all over the world. So this was a project that we piloted in 2019, so just last year, and we were using National Geographic's drop camera system. So that's what you can see very close up in the lower right picture and in several of the others. So we were training MIT students and staff, LINDBLAD undersea specialists, and collaborating scientists in the Galapagos on how to use the drop camera, how to execute deployments in Southeast Alaska and the Galapagos. And our third goal was to build a team for future tech development, exploration, and expeditions around LINDBLAD vessels, which operate in some of the most remote regions of the world. We were planning on doing a lot more of it this year, but unfortunately COVID required us to cancel all of our fieldwork this year. But we're looking forward to expanding on this project in 2021 and beyond, because it was extremely successful. All the participants were very excited about it, and I think there's a lot of potential for being able to use these amazing platforms that get to places where traditionally or oftentimes scientific vessels don't get to go. And the final project is still very much in development. Again, very much derailed by COVID this year, unfortunately. We've been working with Nainoa Thompson and Lehua Kamalu at the Polynesian Voyaging Society. This is a group based in Hawaii that sort of spurred a traditional knowledge renaissance, a Hawaiian knowledge renaissance, starting in the late 1970s and early 80s. And so Nainoa and the people with whom he worked way back then brought back the traditional Polynesian navigation that would have been used to get from Hawaii to Tahiti and all over the Pacific Ocean. And so we've been working with them partly for us to learn more about how they do what they do, and also to figure out how we can combine their ancient navigation, traditional navigation techniques with modern instrument-based exploration. So they're planning several major voyages around the Pacific Ocean in the next coming years, and we're figuring out how to work with them and the Pacific communities to weave together their cultural ties to and knowledge of the sea with going to new places to learn new information about the deep ocean and bring it back to their communities. So that's one project that I'm really excited about. I'm very disappointed that we lost a lot of momentum this year, but everyone's still enthusiastic about the future, and we're trying to figure out how to move forward. So finally, sort of in conclusion, deep sea exploration today is inefficient, elite, and expensive. And as a result, we don't fully understand how to wisely use and protect the ocean so we can thrive today and into the future. But we're able to break down the barriers to the deep sea by combining low-cost technologies, advanced data analysis and access, and capacity building to make exploration more efficient and accessible. So I think the ultimate goal should be to create efficient, equitable systems that can and should be created to broaden access to the deep sea around the world so that we can use the ocean without using it up. And I think we have a few minutes for questions.
Thank you a lot for your presentation.
Absolutely.
So, there's any questions here? Yes, please.
Thank you for your presentation. I have one question regarding the one project that you mentioned, which was, sorry if I pronounce it wrong, but I think it was
That's okay.
MAKA new.
Mm-hmm.
So the capsule that goes to the deep sea. So my question is, how does it, so it has a camera, right? So how does it communicate with the surface, or you have to go down to recover the capsule?
Yep, you have to go down to recover the capsule. It looks sort of like a flashlight or a torch. It's not very big. It has a camera, a pressure sensor, temperature. And so it could, it's really just a camera. So you could deploy it however you want. You could put it on a weight with some buoyancy and drop it down to the bottom. You could scuba dive with it. You can do whatever you want with it. You currently don't have the capability of being able to communicate with the surface. So you would program it before the mission, and there are different modes of being able to record or automatically record. And then when you bring it back, the idea is you put it on a wireless charger, and then it'll use wireless to be able to upload the video and data to whatever device you happen to be using. So you don't have to open it up. You don't have to expose it to, seafloor dealing or seawater dealing with O-rings, all that kind of stuff. So we're really trying to make it as easy to use and low logistics as possible.
I have a question. How are you able to map the entire ocean floor through satellites? Is it just because you can see the currents, and we just through the tides are we able to realize how deep the ocean is in a given area, or like how do we go about mapping the ocean through satellite imagery?
Yeah, it's actually measuring the shape of the seafloor, and you average out all the waves and those sort of ephemeral effects. So the amazing thing is that gravity attracts more water if you have, say, a seamount. So if you have 1,000-meter high seamount, there's going to be more water on top of it. And once you get rid of the currents, the waves, all the other things, the shape of the water around the world is a ratio, or proportional to the shape of the seafloor. And it's something incredible, like centimeters difference of seawater height translates to like 1,000 meters of seafloor height. So the satellites are constantly taking pictures of the ocean and getting those measurements, and then you create a model of the sea surface, and then you can calculate what is the shape of the seafloor look like. So that's when you look at all of these global images of bathymetry. That's usually what you're seeing, is the data from seafloor or satellite altimetry. There is a global initiative right now to map the entire ocean with ships or vehicles or whatever the case may be, to get the resolution much, much higher, tens to hundreds of meters all over the world. It's called the, JEBCO is one of the, it's called Seabed 2030, sorry, is the name of the project. There are a lot of organizations involved if you're interested in that.
For now, I think it's all. I think their center have some questions.
Yes. I mean, Joanna, she's executive secretary from GOM Bonn. She had so many questions that I promoted her as a panelist. Otherwise, it would be very difficult to intermediate questions and answers. So the floor is yours, Joanna.
Thank you, Jose. Hi, I'm Joanna. I'm from their center and also from GOM Bonn. Thank you very much for your presentation. You already answered some of my questions. So as you said, the cruises and the equipment are expensive. So in order that we can monitor a little bit biodiversity and biological observations, we need really cheaper equipment. I was very interested in this project, in this equipment that you talk about, the MAKA new. And I would like to know if after implementation and testing, if you plan to commercially sell it or sell it for research purposes, or how can organizations like GeoBon and, for example, the Earth Center or national government's programs of monitoring can engage with and can have access to this type of equipment?
That's a great question. We haven't quite figured out how to make it accessible to people, but that's definitely one of the goals, is to make these available for people to use, you know, anywhere. So I'd love to keep in touch with you about that. As I mentioned, it's still very much in development right now. We're just ordering the electronics boards like today, and we're doing our first test run this fall, but making them available in large numbers for people to be able to use for monitoring, for exploration, for, you know, whatever your application might be, is one of our top goals.
Thank you. I would like to keep in touch with you if you are available.
Absolutely. Maybe Joao can connect us.
Okay, thank you.
So, Jose,
Oh, it was a fascinating presentation. Thank you so much, Katy.
Thank you for having me.
Absolutely brilliant. You know, there's one question here from Omnia Ibrahim. He's very participative. I think the strong database in archaeology make the person with a good scientific background. How can we move from, this database on archaeology to experiment in scientific observation? That's the base. How can you move from archaeology to deep sea observation?
Oh, it's not hard. I did it. I did my master's in maritime archaeology, and that's actually how I got interested and involved in deep sea exploration in the first place. Was going on a project when I was an undergraduate student to Turkey and the Black Sea to look for shipwrecks. So that's what got me excited about exploration in the first place. And then just being involved and continuing to go on expeditions and learn more about everything, volcanoes, brine pools, all sorts of topics in the deep sea has been really exciting. So I think that, you know, if you're self-confident and interested and want to learn more, that anybody can get involved. And that's really the point, is that it's an exciting field and it's an important field, and we really need more people than just those, you know, small few that have PhDs in oceanography.
Okay. Thank you. I have one last question, but I'm very curious. In the presentation just before yours with Gerard Dooley, he presented this idea of autonomous docking. It's still very complicated to manage autonomous docking in deep sea, but he envisioned in a future, at least in the oil and gas industry, that we could move from one dock to another autonomously, and so they could be shared assets. Now, can you envisage something like that? I mean, the low-cost autonomous docking, where in the future these low-cost sensors could be shared depending on where to connect them? I asking that because we in Portugal, there will be a big project called now listening to the Atlantic Ocean. There will be this new ring, submarine cable ring will be installed with some possibilities to dock instruments on these submarine cables. Do you think it to be possible in the, I'm not saying the near future, but in...
Sure, I think it's possible, and especially in places that already have infrastructure, like oil and gas platforms, like you mentioned. But those are in such small regions, I guess. Like there are tons in the North Sea, there are tons in the Gulf of Mexico, but there aren't many out in the middle of the Atlantic Ocean or out in the middle of the Pacific Ocean. So that's where I think the challenge lies, that I think something like that would be very useful in places where you have the infrastructure to do it. But you know, thousands, tens of thousands of miles offshore out in the middle of the Pacific Ocean might be a bit more challenging to be able to install that kind of infrastructure. So I think it's certainly, anything's possible. That's an engineering problem. That's a money problem.
Definitely, yes.
But logistically, like, does it really make sense? I think is the other
Yeah.
question that you need to balance it with, right?
Okay. So no more question from our side.
Wonderful. Well, thank you everyone so much. This was a wonderful opportunity, and I look forward to, I'm happy to, I saw that some of the other presentations, that the slides were shared, so I'm happy to send a PDF for the presentation if that's helpful, and to stay in touch.
Yes, thank you very much again. Goodbye.
Thank you.
Okay, thank you very much.
Bye.
Okay, bye. Bye.